On a clear night, the sky looks peaceful, a dome of quiet, twinkling stars. Ancient stargazers saw an eternal, unchanging heaven. Yet this serenity is an illusion. Modern astronomy reveals that the universe beyond our eyes is anything but calm. It is, in fact, seething with violent activity. Every star we see is a colossal nuclear furnace, converting millions of tons of matter to energy each second. Even a single gram of starlight energy equals the blast of an atomic bomb. The tranquil sparkle of a distant sun belies continuous thermonuclear fury in its core, holding crushing gravity at bay. We are fortunate that space is vast because cataclysms are happening all the time. Within the reach of the most powerful telescopes, astronomers estimate that on average several stars explode as supernovae each second across the observable universe. Here on Earth, under an ordinary sky, we notice nothing. Cosmic explosions outshine whole galaxies in distant reaches, yet their light arrives as a mere flicker too faint for casual view. Only rarely does the violence burst into naked view. Historical records tell of guest stars suddenly appearing in the sky, shining brighter than all the planets. In 1054 CE, Chinese astronomers documented a new star so brilliant it was visible in daylight for weeks. Unknown to them, they were witnessing a supernova, the self-detonation of a massive star 6,500 light-years away, an event that left behind the colorful Crab Nebula we observe today. Such rare sights hinted that the heavens could indeed erupt without warning. The Crab Nebula, a 6-light-year-wide expanding cloud of debris, is the tattered remnant of a supernova observed by humans in 1054 CE. This beautiful nebula is a scar of cosmic violence, marking where a giant star's explosive death briefly made it visible in Earth's daytime sky. For the most part, however, the universe hides its violence behind wavelengths and signals our senses can't detect. A supernova in a distant galaxy might be invisible to the naked eye, yet shine fiercely in high-energy gamma rays and X-rays. In fact, the crucial news of cosmic violence often reaches Earth in forms of light we cannot see. Fleeting bursts of radiation, neutrino floods, or gravitational tremors in space-time. It wasn't until the 20th century that we developed instruments to catch these whispers of destruction. In the 1960s, military satellites designed to monitor nuclear tests unexpectedly detected potent flashes of gamma radiation coming not from Earth, but from deep space. Astronomers had discovered gamma-ray bursts, cosmic explosions so powerful they outshone entire galaxies for seconds, yet utterly invisible to human eyes. The quiet night was finally understood not as a static backdrop, but as a canvas painted with unseen fire. Our perception is finally expanding beyond visible light. Telescopes and detectors now routinely record the universe's mayhem, the ultraviolet glow of blazing starbirth regions, X-ray flares from hungry black holes, radio shock waves of colliding galaxies. Even our sun, placid yellow orb that it seems, lashes space with eruptions and particle storms. The more we look in new ways, the more we realize that almost every point of light hides turmoil. The cosmos only appears calm because we are small and blind to most of its drama. As the narrator of our cosmic journey, imagine whispering to the viewer, beneath the silence of the stars, something ferocious is always happening. When stars die, they do not go gently. They explode with a force beyond imagination, announcing the end of their life in a final, violent outburst. These explosions, supernovae, are the cosmos's great purge and renewal. In a matter of seconds, a massive star's core collapses under gravity, triggering a shock wave that blows the star's outer layers into space at thousands of kilometers per second. For a short time, the dying star outshines its entire galaxy. To human eyes, it would appear as a sudden new star, as happened in 1604 when Kepler's supernova lit up the night. Most supernovae, though, burst forth in distant galaxies, visible only through telescopes. Yet their energy reverberates across the cosmos. A supernova releases so much radiation that any planet orbiting nearby would be instantly sterilized. In fact, any world within dozens of light years would be wiped clean of life by the onslaught of particles and high-energy rays. One physicist noted that the intense neutrino emission from supernova would be lethal to an unshielded human even billions of kilometers away. Death on that scale defies comprehension. And yet, in a grand cosmic irony, we owe our very existence to it. Supernovae are creative destruction. In the crucible of these explosions, heavy elements like carbon, oxygen, iron, the stuff of planets and people, are forged and scattered into space. Our Sun and Earth are built from the ashes of long-ago stellar catastrophes. Every atom of calcium in our bones, of oxygen we breathe, was minted in a star's explosive death throes. Thus, the universe's violence is not nihilistic. It is the engine of new beginnings. If supernovae are colossal, gamma-ray bursts, GRBs, are downright extreme. These rare events are the most energetic explosions known since the Big Bang itself. A long-duration GRB marks the death of a star even more massive than those of ordinary supernovae, a star that collapses into a black hole and shoots out narrow jets of energy. For a few heartbeats, the burst unleashes almost unfathomable power. In seconds, it radiates as much energy as our Sun will produce in its entire 10 billion-year lifetime. Imagine that all the light the Sun ever produces released in an instant flash. In March 2008, astronomers recorded a spectacular example. A GRB from 7.5 billion light-years away, halfway across the observable universe, that was briefly visible to the naked eye from Earth. Detectors on the Swift satellite showed this burst, cataloged as GRB 080319b, was so bright it would have appeared as a faint star for about 30 seconds if you happened to be looking at that patch of sky. Its intrinsic power was staggering. It shone 2.5 million times brighter than the most luminous supernova ever observed. Had such a burst occurred in our own galaxy, its beam aimed at us, the consequences would be dire. Scientists believe that a GRB within a few thousand light years could strip away Earth's ozone layer and bathe the surface in lethal ultraviolet radiation, potentially causing a mass extinction. Indeed, some researchers hypothesize that a gamma-ray burst may have triggered at least one ancient extinction event on Earth. The universe, it turns out, carries its own cosmic shotguns, fortunately, pointed elsewhere for now. The spectacle of a supernova, or GRB, is both beautiful and terrifying. Picture a massive star's final moments. As its core implodes, twin jets of plasma erupt from its poles at nearly light speed, drilling through the star's surface and into space. In those moments, the star's corpse becomes a celestial blowtorch. High-energy gamma photons race outward, invisible and silent, until they reach our instruments orbiting Earth. Astronomers, who once could only watch supernovae fade slowly over weeks in visible light, now catch these instantaneous GRB flashes and scramble to slew telescopes to their afterglow. In doing so, we have learned that some long GRBs are indeed associated with hyperenergetic supernovae, sometimes called hypernovae, marking the birth of a black hole. Short GRBs, on the other hand, come from another violence, the merger of neutron stars, dense stellar remnants, which we'll revisit later. Our knowledge of these events is still evolving. Each supernova observed, each burst detected, teaches us something new about how the universe works and how it might end. And while these stellar cataclysms are the loudest fireworks in space, they are not the only sources of celestial mayhem. Even after the flashes fade, extreme objects are left behind, cinders of stars and massive black holes that can be more violently unpredictable in their own right. When a massive star explodes as a supernova, it leaves behind a stellar remnant, a condensed core of degenerate matter. In some cases, that core is a neutron star, an ultra-dense sphere the size of a city, spinning and crackling with magnetic energy. Among these remnants lurks a rare type of neutron star, the magnetar, the most magnetized object in the universe. Magnetars are cosmic ticking time bombs. Their magnetic fields are 1 trillion times stronger than Earth's, powerful enough to distort atomic structures and wreak havoc on electronics from 1/4 of the moon's distance. For long periods, a magnetar may seem innocuous, emitting only faint X-rays as it spins. But then, without warning, its immense magnetic field can stress and fracture the star's solid crust in a starquake. The result? A sudden release of energy in the form of a gamma-ray flare, essentially a magnetic volcano erupting on the star's surface. On December 27, 2004, astronomers recorded such an event from a magnetar called SGR 1806-20, located 50,000 light-years away on the far side of the Milky Way. In 1/10 of a second, this magnetar released more energy than our sun emits in 150,000 years. The burst was so intense that it ionized Earth's upper atmosphere from across the galaxy, tripping satellite detectors and briefly expanding our ionosphere. Had this explosion occurred within a few light-years of us, it could have been catastrophic, potentially stripping Earth's ozone layer and causing mass extinction. Think about that. A starquake on a neutron star could affect a planet halfway across the galaxy. Magnetars are like cosmic landmines, thankfully distant, but a stark reminder that even dead stars can bite. Zoom out now to a much grander scale, the hearts of galaxies. Here we meet the quasar, an entirely different beast. Quasars are the brilliant cores of distant galaxies lit by material plunging into supermassive black holes. They are actively accreting black holes on feeding frenzy, each typically billions of times more massive than our sun. As gas and stars spiral into the black hole's gravitational whirlpool, they compress and heat to white-hot temperatures, blazing across the electromagnetic spectrum. A quasar can radiate up to 1,000 times more energy than the entire Milky Way galaxy. Put another way, some quasars shine with the luminosity of trillions of suns. For example, the quasar 3C273, the first ever identified, is about 4 trillion times brighter than the sun, equivalent to 100 galaxies worth of light all packed into a point. Others are even more extreme. Hubble recently found a quasar in the early universe blazing with the light of 600 trillion suns after being magnified by a gravitational lens. These numbers boggle the mind, yet they are measured reality. If supernovae are flashbulbs, quasars are cosmic bonfires that can burn for millions of years. What makes quasars especially violent are the relativistic jets many of them shoot out. Along the quasar's poles, magnetic fields channel some of the infalling matter into tight beams that blast outward at nearly light speed. These jets can stretch hundreds of thousands of light years into intergalactic space, plowing into any surrounding gas. They are so powerful that they can heat up entire galaxy clusters and suppress star formation in their host galaxies by blowing away the cool gas, a dramatic form of galactic feedback. In their heyday, quasars devour matter voraciously. It's estimated that a large quasar's black hole can consume the equivalent of several suns per year, sometimes even per day, as it accretes. Anything that strays too close, a star, a cloud of gas, is shredded by tidal forces into a hot disk swirling around the black hole. From this inferno, energy gushed out in all directions. Any civilizations in nearby star systems would see their night sky dominated by a blinding point of light and space flooded with high-energy radiation. Thankfully, the quasars we observe are billions of light years away and billions of years in the past. The universe's youthful wild years, when galaxies frequently collided and their central black holes rapidly fed. For us, quasars are beacons in the darkness, visible across cosmic time. They also remain mysterious. We cannot directly see the details of the accretion disks and black holes at quasar cores. They are far too distant and small in angular size, so scientists use spectra and ingenious techniques to infer what's happening. We do know that quasars eventually calm down, as their fuel, gas to eat, runs low or feedback blows it away, the luminous engine sputters out. Many galaxies, including our Milky Way, likely went through a quasar phase long ago. Indeed, our galaxy's center harbors a quiescent supermassive black hole, a sleeping dragon that once might have blazed as a quasar and could again if enough matter falls into it. From magnetars blasting gamma rays in milliseconds to quasars shining steadily over eons, we see violence on vastly different scales of time and size. What they share is mind-bending energy and power. They remind us that the universe has engines and triggers beyond our everyday experience. Ultra-strong magnetic fields, event horizons, relativistic jets. And yet, there is one final class of cosmic violence to explore, one that is in some sense even more elusive and profound. Black holes are invisible, yet when they collide, the universe itself trembles. For billions of years, these encounters were completely silent to us. Two black holes spiral together in darkness, orbiting faster and faster, warping space and time around them. No light escapes, no explosion flares, and then, in a fraction of a second, they merge. What is released is not fire, but motion in space-time itself. In 2015, Earth felt one of these distant collisions. The LIGO detectors recorded a faint, rising signal, a chirp caused by two black holes merging 1.3 billion light-years away. In that moment, 3 suns' worth of mass was converted directly into energy, released as gravitational waves. For a brief instant, the power of that collision exceeded the combined light of every star in the observable universe. And yet, the sky looked unchanged. This is cosmic violence at its most unsettling. Enormous energy, no light, no warning. Space itself stretching and snapping back like a struck bell. Since then, we've learned these collisions are not rare. Black holes merge across the universe regularly. Remnants of ancient stars, leftovers of galactic collisions. Even entire galaxies collide. They're central supermassive black holes destined to merge over millions of years. When they do, they will send gravitational waves so large they ripple across galaxy clusters. We are beginning to hear the universe, not just see it, but with every new detection, deeper questions emerge. What happens in the final instant of a black hole merger, where gravity becomes absolute and our equations fail? What lies beyond the event horizon, where space-time folds inward and time itself loses meaning? We don't know. These collisions push physics to its breaking point, into realms where relativity and quantum theory no longer agree. And this may not be the end of cosmic violence. Some theories suggest events even more extreme. The decay of the vacuum of space itself, or phase changes in the fabric of the universe that could rewrite reality faster than light could warn us. These ideas remain unproven, but they remind us how fragile our understanding still is. From a distance, the universe appears calm. But beneath that calm is a history written in explosions, collisions, and catastrophic transformation. Stars die violently to create the elements of life. Galaxies grow by tearing each other apart. Black holes collide and reshape space-time itself. And somehow, from all this destruction, structure emerges. The same forces that threaten annihilation also build planets, stars, and eventually, observers capable of asking these questions. So the mystery remains. Is the universe slowly calming with age? Or is this violence simply part of a much larger cycle we have yet to understand? We listen now, watching the darkness more closely than ever. Because the universe is not silent. It is alive with motion, collision, and change. And we have only just begun to hear its most violent truths.